Okay, so welcome to the next sort of chapter in the course. We last time ended with the row reduced echelon form and a characterization of when a square matrix. First of all, one application was that every matrix is invertible must be square over a general field. We don't need just characteristic 0. And secondly, we then applied it to other kinds of things like a square matrix is invertible if and only if its RREF is the identity matrix, if and only if various other conditions, right? So, so today we start with the next chapter. And so there is, we'll see how far we get. So, okay, let's see. So, vector spaces. So, already we have defined, I have already defined this for you. So, let me start with examples, which we already have also probably seen, but fine, we will see them again. So, the first one is f. Okay, so the first one is f to the 0, which is just defined to be the set of one element, which is formally 0. And 0 is like the origin in the vector space. 0 plus 0 is 0. Anything times 0 is 0. So more generally, let's call this A, let's call this B, f to the n. Actually, I should just write these on the, let's start from here. So this is fine. 1A is fine. 1b f to the n for n bigger than 0. Let's call this f to the d. D is going to stand for dimension. And so this is defined to be a1, a2, ad. And I will just keep calling them column vectors just to be for convention. So column vectors such that ai belongs to f. So all the ai's in. This is literally just the Cartesian product of the set f times f times f. But under the operation, actually I told you the operation already. So these are the vectors, right? And then these are vectors, the set of vectors. But then also you have the set of matrices, where you can do f to the m times n, which is the matrices. And in both of these, on all of these examples, addition is entry-wise, and the scalar multiplication is also entry-wise. C times this vector is CA1, CA2, CAB. Okay. So that's the second example. The third example is, let's see, the third example we also saw. So the complex numbers form a vector space over, you can take whatever, you can take over complex numbers or any subfield contained inside the complex numbers, like the real numbers or the rational numbers. The next one is interesting. I'm going to call it, so I have told you of this example before, but I will state it differently. So fx is the set of polynomials in one variable. Okay, and now polynomials in x are of the form, how do they look like? They look like c0 plus c1x plus so on, right? So you call this c0 plus c1 times x plus dot 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 plus cd times x to the d. Again, d stands for the degree, and here d is of course bigger equals 0, and all the ci's, just like here, maybe I should have called this a0. No, it's not. All the ci's are in f. This is the set of polynomials. It is so it's going to be a vector space. The problem is that not a problem, but if I want to call it vector space, I have to tell you how to add two polynomials, how to scalar multiply. Scalar multiplication is easy. Addition is slightly more subtle. It's really not subtle, but the fact that I want to add two polynomials of distinct degrees, of different degrees. So it's easier when I write it in a different way. And that's what we will do. This is also equal to, I can write this as C0 plus C1x plus dot 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 plus CD x to the d, plus I can keep going 0 times x to the d plus 1 plus 0 times x to the d plus 2 and so on. Let's have that again, all this stuff. Right? So the point is, I can just keep adding zeros. And so this is how I get to my next description. Maybe I'll use a black pen now. So this is equal to, so IE or implies Fx is also equal to the set of all I goes from 0 to infinity, infinite sum, Ci x to the I. And then what I say is all the Ci's are in the field F, and at most finitely many of the Ci's are non-zero. Everything else is 0. Okay? All Ci are in F. Only finitely many Ci are non-zero. Every other Ci is 0. So which means that if you take the last non-zero Ci, I'm not saying everything before it is non-zero, but take the last of the finitely many Ci, which is 0, the largest I. Everything else, all the higher order terms above that are 0. So the polynomial has degree exactly equal to the index of the last non-zero power. Okay, so this is what Fx is. And now once I define it this way, then I can add very easily. Now you can say that now define, I mean, we already defined this, but yeah, so I can say summation Ci x to the I goes from 0 to infinity, plus summation di x to the I goes from 0 to infinity, is defined, a sum of two polynomials is literally Ci plus di x to the I goes from 0 to infinity. And the point is that if everything beyond, let's say, degree 5 is 0 here, and everything beyond degree 200 billion is 0 here, then look at the maximum of the 2 degrees, that's 200 billion. So everything above 200 billion term is 0 here and 0 here. Therefore, the sum is 0 plus 0, and so there's no term beyond that either in the sum. Okay, so that's how you do this. The degree is at most the maximum of the 2 degrees. Of course, you need not be equal to the maximum, because you could have something like x and minus x, and they cancel away and become 0. Or x minus 1 and minus x. They both have degree 1. But when you add x minus 1 plus minus x, you get minus 1. So degree 0. So all you can say is that the degree is at most the maximum of the 2 degrees. The degree is last term. Maybe I should say that. The degree here. Maybe I said that last time. I don't remember. The degree of 0 is, let's say, 0. The polynomial 0. And of a non-zero polynomial. And the degree of summation Ci x to the I goes from 0 to infinity, as long as this is not 0, is the largest I such that Ci is non-zero. Okay, so that's how you write down the degree of a polynomial. Okay. Oh, this was the sum, and of course I have to define the scalar multiplication. That is obvious again. Maybe this should come after the formula for the scalar multiplication, but this is literally again summation C times Ci x to the I. And so you have a coefficient, you have a monomial, and you add them up. And again, you must remember here that if all the Ci's beyond a certain stage are 0, then C times 0 is 0, and therefore that's fine. Okay. Okay, this is a polynomial ring. Okay, that was the example. Did I forget anything? No. The next example we also saw for any set. So I won't write this. I won't write down the scalar addition one, but scalar multiplication, addition, and so on. Yeah. By the way, I should point out that I've been avoiding telling you how to take negatives. Right? A field vector space comes with 3 things. It comes with scalar multiplication, addition, and the fact that there is a negative. But we saw in homework 1 or homework 2, I forget, that minus v is minus 1 times v. Right? So always minus v is minus 1 times v. So if I tell you addition and I tell you scalar multiplication, then I don't need to tell you negatives. That is clear. So that's why I haven't told you. Anyway, so S is a set, F is a field, and you look at the functions from S to F. That's a vector space where the sum of two functions is their pointwise sum at any point. The scalar multiple of the function is the pointwise scalar multiple. That's also fine. Now we come to some interesting examples from matrix theory. So let's do that. Well, two interesting examples. Second. Okay. Now, so two examples from matrix theory. Okay, so given any matrix, so given again M and N are integers, and A is a matrix over a field. I'm going to give you two, I think, yes, subspaces, two vector spaces. Okay, so this is called the null space, which is called kernel of A. The kernel is given by this precisely the set of all X. There's no space to write it. This is the set of X that AX equals 0. So there should X be, A is M cross N, so this should be N cross 1. AX equals 0. And this is the vector space because, well, how is it a vector space? If you type, well, we'll find out. Okay, I'll say. So for example, here you can say that, if you take, if X and Y are in the kernel, then A times X plus Y is AX plus AY by the distributive law for matrix multiplication. When this is defined, they're equal. AX equals 0, AY equals 0, and 0 plus 0 is 0, etc. Similarly, any multiple of anything in the kernel is also in the kernel, and so on. Okay, this is one. The other is called the column space. Which is BP will write as C of A. There's also the row space, and we'll get to that later. Maybe I can tell you that also, but then fine. Column space, I'll tell you the row space later, right? Some people also give this the name null. The rank nullity theorem, you might have heard of that. Okay, this is C of A, column space. You don't need to, yeah, that's fine. This is equal to, this is the set, so these are the vectors that get killed. This is the output vectors. AX such that X in F to the N. Remember now, so this kernel is a subspace of F to the N. Note. So the kernel of A is a subspace of F, well, is a subset of F to the N. I haven't told you what is a subspace yet. But the column space of A is a subset of F to the N. Because you act on a vector of size N, and therefore you become a vector of size N. Okay, fine. So this is some examples. You can check again that these are vector spaces. They are more, they are what is called the subspaces. So I will say in fact are subspaces. Now I have not told you what this means, so I will tell you. So definition. Yeah. Definition. Okay, a subset of a vector space is a subspace. So first of all, it must be a subset. But of course, not every subset is a subspace. So when is a subset a subspace? It is so when it is a vector space itself under the same operations as V. Under the vector space operations in V. Let me give you an example. So as I told you, the very first example I told you was f to the 0, right? F to the 0 is a one element vector space. So in particular, I can take any element of a vector space. I can take like in f to the n, I can, or in f. And so f is a vector space over f. For example, the element 1 belongs to f. So I can take this 1, this is a singleton subset. I can say this is a vector space. What is the operation? The operation is that this is the origin. So this plus itself is itself, anything else this is this, and so on. And that absolutely gives me a vector space. The problem is it is not a vector space under the same operations as the field. 1 plus 1 does not equal 1 in the field. You can define it to equal 1, but then you are not sitting inside the field operations. You are using different addition. You are calling this like 1, but you are really thinking of it as the origin, so you are saying 1 plus 1 equals 1. But that then becomes the origin in the vector space. It does not stay as the 1 in the field. 1 plus 1 is not equal to 1. Okay? Because 1 plus 1 is 1, you cancel the 1, you get 1 equal to 0. That is not true. That is impossible by the field axiom. Right? So that's why you can put a vector space structure on it. It will just not be the same operation as in the original vector space, as in the original field. So that's when you call it a subspace. Okay? Yeah, so for another example is, for example, you can say that, look, here's the x and the y axes. These are actually subspaces. Okay? So for example, let me maybe even say that. I'll give you two examples. Okay, so 0 in F is a subspace, as I told you, is an F vector subspace. But 1 is not. Similarly, I can say that inside R2, if you look at the x-axis and the y-axis, so the x and the y-axis are subspaces of R2. But the line y equals 1 is not so. What is the line y equals 1? It is precisely the line, you draw a point 1 and then look at all the points of height 1. This is clearly a line. Y equals 1 is a line parallel to the x-axis. So it's clearly a line, and therefore lines are vector spaces. If I multiply, if I take this vector and I rescale it, I get this vector and so on. The problem is then the origin is here, not here. So you're shifting the idea is you're not having the same operations, you're not having the same elements. The 0 in this vector space R2 is not the 0 in this line, if you think of this line as a vector space. Therefore, this line is not a subspace. Maybe I should call this in B. Okay, so this blue line, y equals 1, is not a subspace. But of course, the x and the y axis are subspaces of R2. Okay, so that's an example again. Okay, great. Now what next? What's that? Okay, great. Now, the moment I say this happens, it means, so what does this mean if it's a vector space under the operations? It means, this means that first of all, this must, so the zero element must be inside W. Because the origin must lie inside any vector space, right? So the origin of V in those operations must lie inside W, and W is closed under plus, minus, and dot, the scalar multiplication, right? Meaning, if you take W1 plus W2, if you take two vectors in W, then their sum is in W. If you take any vector in W, its negative must be in W. And if you take a vector in W and a scalar, then the scalar multiple must also be in W. So when I say it is closed under, it's a vector space under those operations, it means that it must contain the origin, it must be closed under addition, scalar multiplication, and negatives, not negation. Okay, fine. So that's the definition of a subspace. We saw two examples. Yeah, that's fine. That's good enough. I mean, I can tell you more. So certainly, we saw other examples here. So R or C. So R is a subspace over any of the fields that R contains. So either R or Q. And so it's a Q vector subspace, it's an R vector subspace. Okay, one more maybe. Which one? The XY. Okay, these. Good. I'm actually going to come here. 4 is 0 is a subspace, of course. 0 is a subspace of any vector space. And every vector space contains the origin, and you can check that 0 is indeed a vector subspace with those same operations. Is a subspace. I'll just see it here. Is a subspace. Okay, and number 5. 5 is also interesting. I'll say it just above. V equals F to the n cross n. Let me erase something. Taking up too much space. So 5. V equals square matrices over a field. And W equals the set of all upper triangular matrices. Let's call this W1. And then W2. Lower triangular matrices. And W3. W3 is of course diagonal matrices. These are all subspaces. And note here that W3 is what are diagonal matrices. Again, if you did homework too, you know they're precisely the matrices which are both upper triangular and lower triangular. And so this is exactly equal to W1 intersect W2. And actually, that's a very useful recipe to create additional subspaces from older ones. You intersect some subspaces, you still get a subspace. We will get to that. Okay, but now that was example 5. You can verify this, and there's nothing much to do. Example 6 was exactly these row space and column, null space and column space. These are also subspaces. So, so let's say given A, let A belongs to F to the n cross n. So part A, null space, the null of A, which is the kernel of A, is a subspace of F to the n. Okay, and similarly, the column space is a subspace of, that's fine. F to the n, as we noted. Then you can verify this, right? Because now you can verify this by hand, like check that all the operations hold. Or to verify that something is a subspace, you can be slightly sneakier, you can be slightly clever. Right? You can verify this using very simply the fact that, okay, I'll tell you the verification later on. So let's say, so 7, the set of constant matrices. What does constant matrices mean? It means every entry is equal. And here I don't need to take them to be square. I can take any rectangular matrix like here, contained in F to the n cross n. Right? Because if you take a scalar multiple of a constant matrix, it's still constant. If you take a sum of two constant matrices, it's constant, and so on. So this is a subspace. Another one is here is a nice one. Let's take F to be R. Okay, and I take the set of all. So the biggest space is a set of all functions from 0, 1 to R. All functions, okay, no restriction. This contains, as a subspace, the set of all continuous functions. F from 0, 1 to R continuous. Okay, and this further contains F from 0, 1 to R differentiable. So these differentiable functions are a subspace of continuous functions. Because why? Because they are a vector space in their own right. If you add two differentiable functions, you can take the derivative. If you scalar multiply a differentiable function, of course again you can take the derivative. So these form a vector space under the same 0 and sum operations as all functions. If you add two continuous functions, then it's continuous. If you scalar multiply, it's still continuous. So indeed, these are also a subspace of all functions. This is a nice set of subspaces. And the last example I will give you is that of polynomials. We even over a general field. But I will say let's say the degree is at most 5 or the degree is at most 2. So let's say quadratic or linear or constant polynomials. So let's call this example 9. So I don't know. Let's call it f of x in px in fx such that the degree of f, this is a subspace of the set of polynomials itself. Okay, so how do you prove such a statement? Again, I'll give you a way to prove all these things in a minute over here. But so, for example, I can take, for example, let's say I take the second degree or less. So that means I'm looking just at C0 plus C1x plus C2x squared. All the Ci's are in F. The claim is this is a subspace of the set of polynomials. And indeed, when you add two polynomials which look like this, and notice I did not say that C2 is non-zero. I did not say the degree is exactly 2. Degree can be 2 or 1 or 0. So when you add two such expressions, C0 plus this plus this plus D0 plus D1x plus D2x squared, then you get C0 plus D0, constant term, plus C1 plus D1 times x, linear term, plus C2 times x plus D2 times x squared, quadratic term. And similarly, when I multiply this by a scalar, the scalar gets multiplied to every single coefficient. So indeed, this is a vector subspace of this thing, the set of all polynomials. Okay, great. Of course, notice, so maybe I should say that, note, the polynomials f with degree of f exactly equals, what this is less equals to. What if I take degree of f to be exactly equal to 2? Well, or exactly equal to d? This is not a subspace. Unless d equals 0. D equals 0 are the constant polynomials, and constant polynomials are literally the same as their scalars, right? So they form a subspace. But if I take degree 2, let's say, or linear, so if I take degree 2, I can take an x square, and I can also look at minus x square. And when you add them up, you get x squared times plus minus x squared is 0. But 0 doesn't have degree 2. 0 has degree 0. So therefore, this doesn't work unless d is 0. For d equal to 0, it's a subspace. Okay, so now let me tell you the lemma. So lots and lots of examples of vector spaces sitting inside vector spaces with the same field, with the same vector space operations. And that is when they are called subspaces. So now instead of verifying that something is closed under all the field operations and it contains -1 times the element and it contains the origin and so on, here's a simpler way to do it. Then proposition. A subset W of a vector space. I won't write that V is a vector space. Is a subspace if and only if the following very simple condition holds. How do I want to say this? Oh, it's not the previous page, is it? I call it a lemma, it seems. Anyway, if and only if C times W plus W prime is in W whenever W and W prime are elements of the set W and C is a scalar. This is very useful. It's just saying that, just check that this condition holds for general vectors W and W prime in your subset and general scalar C. Then that subset is actually a subspace. So prove. Maybe then I can even tell you how to check these things. Right? So before we prove this, let's look at this condition and let's apply it to upper triangular matrices. Right? So if you have two W1 and W2, W and W prime, which are both upper triangular matrices, and you have a scalar C, then what can you say about C times upper triangular matrix? Well, the entries below the diagonal are still C times 0, which is 0. So it stays upper triangular. Now, what can you say about CW, which is upper triangular, plus W prime, which is also upper triangular? Well, again, you're adding two entries below the diagonal, both of which are 0, that stays 0. So a sum of upper triangular matrices is still upper triangular. Therefore, this condition is satisfied, and therefore you trivially see that the set of upper triangular matrices is a subspace of all matrices. And similarly, for example, for null space, you could literally write down that if since X, suppose W and W prime belong to this thing, and C belongs to F, then C times. So how do you check that CW plus W prime is indeed in the null space? Well, the null space is defined to be the vector scaled by A. So let's look at A times CW plus W prime. What do you get? Well, by associativity and this and that, you can check that you get C times AW plus AW prime. But what is AW? Because W is in the null space, A times W is 0. The vector is 0. So C times the vector 0 is still 0. And similarly, A times W prime is 0. So this is C times 0 plus 0, which is 0 plus 0, and that is still 0. And so because A times CW plus W prime is 0, therefore CW plus W prime must belong to the null space as well. Therefore, the null space satisfies this condition, and hence it is a subspace. So that is how you verify that certain subsets are subspaces. And the same thing for any one of these conditions. And C times W plus W prime. If W and W prime are differentiable functions, then the constant multiple of W plus the other one W prime is still differentiable because you know the formula for the derivative. CW plus W prime derivative is C times the W derivative plus the W prime derivative. Right? So you can just write this down. So because of that, this lemma is very, very useful in checking that every one of these examples is indeed a subspace of the given vector space. Okay, the proof also is very easy. Right? So suppose the proof, let's do the proof in black here. Yeah. The proof is, yeah, so let's say this way. This is clear. If something is a subspace and W prime are in W, then W belongs to W implies that scalar multiple of W is in W, and then W prime belongs to W also implies that this and this together implies CW plus W prime in W, because the vector space is closed under addition and scalar multiplication. Okay. The converse is slightly longer, but not very long. So first of all, I want to show that the vector space is closed under addition. And I only have this condition is true for all scalars C. So put C to be 1, then I get the addition, right? So W plus W prime is in W if W prime in W by setting C equals 1 in this. Let's call this condition star. By setting C equals 1 and star. Okay. So indeed, my subset W is closed under addition if it satisfies this condition. What else must I check? I must check it's closed under scalar multiplication and negatives, and then zero vector, right? So okay, fine. This is one thing. Secondly, yeah, set C equals -1 and W equals W prime. Okay. Similarly, set C equals -1 and W prime equals W. What do we get? We get minus W plus W equals 0 belongs to W prime. So it implies 0. The zero vector of V, at the origin in V vector space, belongs to W as well. Then now set C equals -1 and W prime equals W, you get minus W's. Sorry, now set C equals 0. And W prime equals W. Sorry, something is very wrong. W prime equals, we don't know that it's closed under that, so that's fine. Now, okay, we know that 0 is in W. So now set C equals -1 again. And W prime equals 0. Then what do we get? We get minus W plus 0, which is in W. So W is closed into the negatives as well. And finally, we can do the scalar multiplication by, again, the same thing, but now you just set C to be C. Set W prime equals 0. What do we get? C times W is in W. So indeed, the set W is closed under addition, under the origin, under negatives, and under scalar multiplication. And any set that's closed under those is a subspace. Therefore, W is a subspace. So this is a very useful way to prove that something is a subspace. Right? It's just it simplifies the calculations, which is very nice. Okay, so that is that. So done. This is what. So now let me tell you two ways to build subspaces from build new subspaces from old ones. I told you lots of different subspaces here as examples, but now I'm going to give you two structured methods to build new subspaces from old ones. I'm always reminded of Aladdin and the magic lamp, and you build something new from old. Anyway, so yeah, so I'll try to write some more black pens maybe. Okay, so definition. So, okay, maybe just as an example first. say W1, W2 are subspaces of V. Okay, V is a vector space. W1 and W2 are subspaces of V. Okay, fine. Then, if you look at the intersection, it's not hard to prove that this is a subspace, especially using this lemma. I won't say of V, that is obvious. But there is a different construction which is less obvious, and that one I will tell you now. That's called a sum. What I do is I take one vector from W1 and one vector from W2, add them up, and look at the collection of all these possibilities. The claim is that is also a subspace. So also implies that the set of vectors W1 plus W2 such that Wi belongs to Wi for I equals 1 and 2 is also a subspace. There's a name for this. This is called W1 plus W2. So the claim is that this vector space, this set subset of V, these are all sums of vectors in V. So every one of these elements of W1 plus W2, every one of these guys is an element of V. The claim is this is a subset of V, this actually is a subspace of V. That's the claim. So more generally, so you can prove this in general, we can define this in general and prove. Let us do that. The intersection is clear, its intersection has sets. So let's define this using, let's define the other one, the sum. So more generally, okay, let's write down definition. And now I'm going to define this sum, it's called the Minkowski sum, I guess, not just for 2 subsets, not just for 5 subsets, but for an arbitrary collection of subsets, finite, infinite, whatever, it doesn't matter. Just for fun, because, well, just for convenience, because we will only deal with this concept for subspaces, I will define that, I will assume that the subsets are subspaces. So given subspaces, although, as I said, this could work for subsets as well. I belongs to I of an F vector space V. Okay, their Minkowski sum is it's somehow defined in a similar way to what we defined for polynomials, where all but finitely many things were 0 kind. The Minkowski sum is, so the symbol is summation Wi, I belongs to I, and the definition, you can define it in 2 different ways. First of all, this you can write down is Wi1 plus Wi2 plus dot 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 plus Wik, such that k is bigger equals 0. If k is 0, then this is the empty sum. And the empty sum is defined to be 0. And Wij isn't Wij. Wi1 isn't capital Wi1, and so on. This is the definition of the Minkowski sum. But you can define it in a slightly different way. So notice a note or remark. So this is the definition just like we first defined the polynomials. C0 plus C1 x plus C2 x squared plus dot dot plus CD x to d. But then we said that this is also the same as just summation from I goes from 0 to infinity. Ci x to vi, the at most finitely many terms are non-zero. And now because each of these is a subspace, clearly it must contain the 0 element. The 0 element of V, the origin in V, must be contained in every subspace. So if I could take 5, I could take the sum of one element from every Wi and add all these infinitely many elements up. But I could say that I must insist that only finitely many of these are possibly non-zero, and the rest of them just have you choose the zero vector forms, plus 0, plus 0, plus 0, plus 0. That's what it really means. So this is essentially equal to is basically I write because one has to write things down precisely. So that's why I said basically equals the set summation. Now I'll write it on the next line. This basically equals the set of all sums, and this time the sum is not over just 1 to k. This is the sum over all I, wi, such that wi is of course first of all a vector in wi for all I, and then but what next? At most finitely many of the wi's are non-zero. For all but finitely many wi equal to 0. Zero meaning the origin in the vector space V. So I just write 0 subscript V. Okay. This basically equals that vector. Okay, so that is good. Okay, great. So that's the definition of the Minkowski sum. And of course, you have the intersections. Now here is the proposition. We have to use a black pen. I will stop writing proposition. I'll just say prop n. Okay, so given an f, so now I'm given an arbitrary, given all of these things. So, given subspaces. Of an F vector space. So we want to say two things. We want to say first of all that this thing is not just a subset, which we have defined this way. It is a subspace. And similarly, if you have here, similarly the intersection is also a subset, but in particular a subspace as well. So those two things we want to say. But we don't want to just take the intersection over two subspaces. We want to take it over an arbitrary collection of subspaces and claim that still gives us a subspace. As far as this goes, yeah, this one we have to still do in this nice way. It's not difficult. You can't add up infinitely many non-zero vectors, but you can add up finitely many of them and just put 0 in all the other places. So first of all, we want to claim that for arbitrary sizes, not just two element sets, arbitrary numbers of subspaces, their intersection and their Minkowski sum are both subspaces. That is the first part. That's the crude version. The more sophisticated version is that it is not just a subspace. It's like, like if you have 6 and 12, then you can say that 3 is a divisor of 6 and a divisor of 12. But so is 1, so is 2. They are all divisors of 6 and 12. The nice thing about, and similarly so is 6. Right? The nice thing about 6 is that 6 is the greatest common divisor. So that's more than just saying divisor. Similarly, the intersection is a subspace, but the intersection is like the largest subspace sitting inside all of them. It's like the greatest common divisor of all the wi's. Okay? And similarly, the summation is like the least common multiple, or the smallest subspace that covers all the wi's. Okay, so I'll write these down over here. Okay. So these are the given conditions. Now, point 1 or part A. Let's call it part A. Just in case the proof has parts. is 1. The intersection I in I, Wi, is the is the largest subspace. Is not, so first of all, this means it's a subspace, but it is much more. It is the biggest one of V that's contained in all W. Okay, and similarly, this one. If you look at the summation of the Wi, this is the smallest. This is like the greatest lower bound, the infimum, if you will, or the GCD. This is the least upper bound, or the supremum, or the LCM. Exactly parallel is the smallest subspace of V that contains all the Wi. Now, what does it mean to be largest and smallest and so on? Let's look at this one. Is the largest subspace of V that is contained in all the Wi. It means if you take any other subspace of V that is contained in all the Wi, then that subspace must be contained in the largest one. It itself is a subset of the intersection. That is almost trivial. This one is, I mean, it's also sort of trivial, but slightly less. So we will write this. We'll write down these proofs in detail, but yeah. So, but in some sense, I essentially want to say IE. This is the theorem. So the intersection of, so this is literally like the greatest lower bound and the least upper bound. If you take any I0, a single individual entry in I, and then the less equals, I mean subspace of, or included in if you want. And this is true for all I. And these are the best possible lower and upper bounds that hold such that this equation holds. These containments hold for all I know. Oh, so in some sense, that's why I sort of called it the greatest lower bound, infimum, and this I call the supremum in the sense of real analysis. Or I could call this some kind of like the GCD and the LCM. And there is a nice analogy to the GCD and LCM. Sorry, maybe I'll just say, I'll mention this. Where is the blue pen? Let's call this 1 and let's call this 2. And let me elaborate on what the 1 and the 2 mean. What does it mean to be the largest subspace contained? I said it just now, but I'll just write it out. So 1 means, and 2 means. So 1 means if there is any subspace, if U is any subspace of V, the same thing here. Containing, so such that U is contained in all the Wi. Then U must be less than the greatest lower bound. So U is contained in the intersection. And here, if U is any subspace of V such that U contains all the Wi, then U must be bigger than the greatest lower bound. That is the statement. Okay, let's prove these. I mean, the proofs are not very hard. Maybe the notation is the hardest part of this. But it's literally just say take sums of vectors. And the point is these are the important constructions because they give you the greatest lower bound and the least upper bound. Intersection is easy. The summation is sort of maybe you might not have seen it before. But once you see it, it's not that hard. It's like just intuitively clear. So prove. Again, let's first start with part 1. Part 1 is sort of easy. So first of all, I want to claim it's a subspace and then it has this largest property. Okay, so part 1 is easy. So I won't do this. Maybe I will. So in some sense, by the way, it's interesting. If you have then I won't do this. Okay, let's just do it. So let's do this. So I'm going to use the proposition, the C times W plus W prime proposition. We are saying we will use the CW plus W prime proposition. Okay, so now how do we use it? Well, here is the one. So let's start with part 1. So suppose I have two vectors in this intersection. First of all, I want to prove it's a subspace. So say W and W prime belong to the intersection of all the Wi's. And C is a scalar. Then, that means they belong to every single Wi. If you look at C times W plus W prime, this itself belongs to every single Wi. Because W belongs to Wi, W prime belongs to Wi, Wi is given to be a subspace, and C is a scalar. So therefore, this thing belongs to Wi for all I. And therefore, it belongs to the intersection. And if something is common to all of them, then it is in the intersection. Definition. Okay, great. So that means it's a subspace. So by the proposition, so by the above proposition, the intersection of Wi is a subspace. And then this part is almost trivial. If U is any subspace such that U is contained in Wi, then by set theory this happens. I'll just call this star star and star star rows. Star star trivially rows. So this ends the proof of part 1. And part 1 is obvious. It is a subspace and it is indeed the largest subspace in that sense. The part 2 is slightly trickier just because of the notation. The concepts are really this pretty much no hardware at all. Let's keep this. So first of all, again, how do you say it's a subspace? Very good. Okay, fine. So how do you say it's a subspace? Well, okay, you can write on either of the two descriptions. One is that it's a finite combination or it's a full combination with at most finitely many terms 0. So I did it which way? I did it using the infinite, the full combination. So again, let's do that. So 2, say W equals summation Wi and W prime equals summation W prime I lie in summation Wi. Right? I want to do the same thing, and C is in scale. I want to do exactly the same kind of thing. We will still use that same lemma. Okay, so I want to say C times W plus W prime is in the same summation Wi, is in the same subset. How do I do that? So let me just record some data. So as I said, at most finitely many terms are non-zero. Right? So let us denote by capital J the subset of these I for which Wi is non-zero. So denote by let J consists of the I such that Wi is not zero, and similarly J prime. These are both finite sets because that's the definition of W prime. So J and J prime are finite. Which means that J union J prime is finite. Right? The union of two finite subsets of I is still a finite subset of I. Now what happens when you take C times W plus W prime? So first of all, yeah. And we may also write you see, instead of taking the sum over all elements of I, if there are most of them are 0, then I can just take the sum over Wi is summation over I in J. Because everything outside of J, the Wi's are 0. So therefore, I can similarly write W to be the summation of I in J Wi. I could take any larger set than that also. And that is not a problem because every extra index in here, that Wi is 0. So if I add finitely many 0 terms, that doesn't change. So I will actually take a larger set, namely J union J prime. And W is equal to that. Similarly, W prime is also equal to this set of. So you would normally say J prime, but now I'm going to say again J union J prime, W prime. Because everything outside of J prime, such as the elements of J outside J prime, those W prime J's or I's would become 0. That's the definition of J and J prime. Okay, great. So now we are almost there. So now what happens when I take C times W plus W prime? It's exactly the same thing. And the point is J union J prime is finite. This is the key. This is the key. Let's write down C times W plus W prime. Using these two representations, now they are both being summed over a finite set. And so I just have summation I in J union J prime C Wi plus W prime I. And indeed, because each Wi is a subspace, this guy is an element, it's a vector in W. And this is true, and this sum is finite. So indeed you have this thing, and you can add plus 0 for every other element of I. So therefore this is indeed in the summation of W. And it's a sum of vectors in Wi in the ith component over finite indices. And that's by definition in the Minkowski sum of all the Wi's, not just the ones over J union J prime. Because I just take 0 vector for every one. So that proves that Minkowski sum is a subspace. Now I want to prove this smallest one. So why is this true? Right? So the point is you can again do the same thing. Suppose U is anything true. So then maybe I won't even, I'll just erase this and now just write that up. Now suppose next, suppose U is any subspace or V such as subspace. I want to prove that U must contain the Minkowski sum. Okay, fine. Let's do that. Then now here is maybe where I use the other description of the W. So I take I1 plus I2 plus I3, right? So I want to say that U contains every element of W of the Minkowski sum. So given an element of the Minkowski sum, given Wi1 plus dot dot plus Wik. Okay, U is any subspace. So if k equal to 0, then this sum was defined to be 0. 0 is clearly contained in U because U is a subspace. So I want to just show that this element of the Minkowski sum with k bigger than 0 and each Wi j belongs to Wij for all j. So I'm given this thing, given a typical element, given any element in here, either that element is a 0 element but the zero element belongs to any subspace by definition. Or that element looks like this for a positive number k. And I want to prove that this must lie in U. Okay. But that is also easy because I know that each of the individual guys lies in their respective component, which lies in U. And U is a vector subspace, so it must be closed under addition. So if you have all these vectors lying in U, then their sum lies in U. It follows that. It follows that their sum lies in U. And therefore we are done. That I'll just say this. Right. So therefore every vector in this set lies in U, i.e. the set is contained in U. I.e. this Minkowski sum must be contained in U. And that was what we wanted to prove. Okay, that is the end of the proof. So I'll take a small break, like pause here for, you should pause the screen if you want, but because I'm going to erase stuff. Okay, so that is the end of that part of abstract vector spaces. You have vector spaces, we did lots of examples, and then we saw two constructions. One is sort of like the greatest lower bound of a bunch of subspaces, it's just the intersection, and one is the least upper bound of a bunch of subspaces, that is the Minkowski sum. And we said that they were really the greatest lower bound and the least upper bound. Okay, so now we start with sort of the theory of. So this was sort of very abstract. Now we get more concrete. We talk about spanning sets, linear independence, and dimension and basis. Okay, so that will occupy, of course, this class and the remainder of this class, but then also the next class. We have about 20 minutes or so. I'll find a good stopping point and stuff. Okay, maybe I should switch back to blue. Okay, so span. The definition. Okay. So I'll give you a lot of definitions. First of all, I'll define, since I don't think I actually defined it, what it means to be a linear combination. So okay, so let's say V is a vector space over there. A linear combination or a finite linear combination of elements of V. Yeah, I mean, so let's see. So all linear combinations in this course will be finite. Until you go to like power series or Fourier analysis, combinatorics. Yeah, started writing combinatorics. Combination of, let's say, V1, V2, Vk in V. Okay, I'm underlining the vectors Vi because I'm going to differentiate between those vectors and the scalars. Is a sum C1 V1 plus dot 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 plus Ck Vk. V, obviously, where all Ci are scalars. Okay, so a finite linear combination of V1, V2, Vk belonging to V is a sum of the form C1, V1 plus C2, V2 plus dot 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 plus Ck, Vk, which is obviously a vector in V as well, where all the Ci are belonging to F. Okay, now the span of a set, now take any subset. Maybe I should first define the span of, okay, I'll do that later. The span of any subset of V, of any non-empty subset of V, is precisely the collection of finite linear combinations of elements of this set. I should give it a name. This is span of S. Okay, again, I will write it down in two ways, just like the Minkowski sum. Okay, so it's span of S. There's two ways to write it. This is the set of all such linear combinations. Summation Ci, Si, I will call it Si. I'll underline the S because this is a vector, such that Ci is a scalar, Si vector is an S for all, and K is any non-negative integer. So again, if K is 0, then the empty sum is defined to be the 0 vector. Okay, maybe I should at this point switch pens again. Now let's to a new pen. Okay, oh, this is not full stop because there is a different definition as well, and this is exactly the same definition like in wherever else I said. So basically, you just say take the sum over all S in S and some coefficient Cs times S, where Cs is in F, and only finitely many are non-zeros. At most, finitely many Cs are non-zero. So this is the span. Okay. This was the span of a non-empty subset S. So of course I must tell you what is the span of the empty set. If you take the empty set, the definition of the span of S is it is precisely the element 0 of a vector space. So there's a 0 vector. The span of the empty set is 0. It is all possible linear combinations of nothing, but that does include empty sums, and empty sums are by convention taken to be 0. Okay, so I think the next thing is just this obvious statement that the span is indeed a subspace as well. So remember, we define vector subspace, but so the span is a vector subspace. Fine. Yeah. And in fact, again, we can do something like this biggest, smallest thing. Lemma. This is fairly easy, so it's called lemma, I guess. Given any S containing B, a subset, either the empty set or non-empty set, the span of S. Sorry, I don't need to say the span of S, I should just say span of S is the smallest subset of S, subspace of V, I need to get space, containing S, or that contains S. The first claim is it's a span. The fact that the first claim is it's a subspace, that basically comes from here, right? If there are only finitely many that are non-zero, or if you add a finite linear combination with another finite linear combination, then you're fine. Or if you do this, I'll just do the second one. So given W equals summation CSS and W prime equals summation C prime SS. Right, so scalar times vector, of course S in S, S in S, and C a scalar in the field. Then you can compute again. C times W plus W prime is summation S in S. Sorry, this is not CS. C times CS plus C prime S. Just associativity or whatever. The point being, you can do this because, of course, all the sums are finite. These are all finite sums. Because both are finite. Because W and W prime are both finite sums. So that's why they're finite sums, so you can do this. And now, but therefore, well, this is still in the span of S. Because this itself, if those two are finite sums, then this is a finite sum. So span of S satisfies that proposition property that if you W and W prime lie in it, then C times W plus W prime lies in it. Therefore, span of S is a subspace. Why does span of S contain S itself? Because I can take 1 times S plus 0 times everything else. So this is part A. Part B, set. So sorry, given S in S, set CS equals, given S naught in S, set CS naught equals 1 and CS equals 0 for all S not equals the specific element. Then what is this infinite combination? It is 1 times S naught plus 0 times the rest. So let me write that down. So if I have CS in S, for this particular choices of C, then how much is this? On the one hand, this is equal to CS naught times S naught, which is 1 times S naught plus 0 times the rest. On the other hand, this is of this form because it's a finite sum, right? There's only one term, so it's a finite sum. And therefore it must belong to the span of S. So in particular, every element S naught in S belongs to the span of S. So S indeed contains, span of S contains S. So this. That is part B. So it is a subspace of B, it contains S, and now I want to say it's the smallest. So well, that is again, maybe that one I'll leave to you guys as an exercise. It's exactly the same kind of thing as we just did. So the smallest part, exercise. Yeah, that sounds like a good idea. Exercise. Yeah, so I mean, it's basically exactly along the lines of the smallest and biggest that we just did. So you should try it on your own. Okay, so now that's the span. At some point I have to figure out where to stop. I should do examples of the span for sure. Without that I cannot stop. Maybe I will stop after the examples of span. And we will start with linear independence next time. So today is a slightly shorter class, but not much shorter. I had a slightly longer class last time. So basically, the span is the set of all linear combinations. So yeah, so let's do examples of span. Okay, so I mean, you can do all kinds of things. So first of all, let's say the span over the real numbers. By the way, sometimes you don't just say span of S. Sometimes you want to specify the field itself. Like this is span, the F span of S, like this. Okay, like this span. So I'm just saying span R so that you know for yourself. You already know that the field is the real numbers. Let's look at x, x cube, x fifth, and so on. This is precisely the vector space of odd polynomials. Or odd polynomial functions, actually. Luckily, R is an infinite field, so polynomials and polynomial functions are the same thing, but I won't tell you that. I won't elaborate on what that means. But this is sort of just odd polynomials. Okay? So, why? Because every polynomial which is odd must contain only odd degree terms. So and it must contain only finitely many terms. So it's a finite linear combination, like C1 x to the 1 plus C3 x to the 3 plus C5 x to the 5 and so on. It's a finite linear combination of exactly these odd degree monomials. Although there are infinitely many of these monomials, the number of them you use in any actual polynomial is a finite number. That's why it's a polynomial. That's why it's exactly the set of all. Okay. So yeah. Okay. Similarly, let me tell you. This is nice. the span of, so let's say over any field F of the following matrices: 1, 0, 0, 0, 0, 0, 0, 1, and 0, 1, 1, 0. 3 matrices. So what should the span be? So maybe you can pause the video for a couple of seconds and you can try to figure out what this is. And so, okay, great. So if you figured out something, then you are well done. And for those of you who just want to enjoy the show, so what is this? So let's actually prove this. Right? So this is equal to A times the first matrix. This is a bad pen. Plus B times the second matrix. Plus let's say let's say C times the second matrix. This is the worst then. Plus B times the third matrix. Right? Such that A, B, and C are scalars. Okay, right. This is literally the set of, well, this is a finite set, so this is literally the set of all possible linear combinations. But now let's write this down. What is this matrix? This is exactly A in this place, C in this place, and B and B here. And this is, well, you know what these are, right? These are precisely the 2 cross 2 symmetric matrices. Over the field F. That's the set. So there's something to be said here, which is that here are 2 different. So the span of this, of course, is a subspace, is the smallest subspace containing these 3, and so on and so forth. The thing to be said here is that there are 2 descriptions of the same object here. And so this is description 1, this is description 2. One is explicit or descriptive. Right? It's an explicit description of what that object is. It is the set. It is the set of matrices that look like this, or descriptive. And the second is sort of a conceptual one. It's a set of symmetric matrices. Okay, so in maybe in homework problems and so on, maybe in the midterm or the final, if I ask you, compute the span of some set, I would like you to give me the descriptive one, the explicit one, and also, that is just easy, right? That will literally plug in the definition of a linear combination. There's nothing to do there. But I would also like you to give me the conceptual description. I mean, give me or give the TAs in the homework and so on. This is 2 by 2 symmetry. You must understand, you must recognize. What is this? This is ABBC. Fine, great. That's an explicit formula. But what does that mean? What is the meaning of ABBC? It means exactly that that matrix is symmetric. So that's what you should also write down. So I want to see that you know what the final answer actually means. It's not just some math class where you work out some calculation and you give the answer. No. The answer is 0.3. That doesn't help. The answer is 2 by 2 symmetric matrices. That means you know what's going on. So that's what I want to see. Okay, great. So I think maybe that is okay. I'll just mention a few more spans and then we will stop. So this is the example. Now, let me mention 2 or 3 more spans, and then just for your reference. So if you look at now the span of, this was example 2, so example 3. Span over the real numbers of 1 and this I, which is the square root of -1. So is the set again. So you can write this down again in the set of all the same way. You can write this is the set of all A plus BI, that A and B are real numbers. So this is indeed the descriptive one, the explicit description. But I want the conceptual one as well. And of course, we all know what the conceptual one is. It is the field of complex numbers. Okay, That is summary 3. So the example 3. And now example 4. I think that may be my last one. Given A in the given any matrix over any field of any size, if you look at the span of, maybe I'll just say only one of them because I haven't told you the span of the rows. The span of all the columns let's say A equals something. Let's write these like U1. There are n columns. Span of all the column vectors of A, columns of A. How much is this again? So again, let's work this out first by the descriptive way, explicitly, and then by the other way. This is equal to the set of all C1U1 plus C2U2 plus CNUN. So oops, this is not vector. Such that all the CIs are in the field. So far, so good. This is explicit. Now, how do you right, remember, I gave you something called the column space, right? It is natural to ask, this is the span of all the columns. Does that have some relation to the column space? But what was the column space? The column space was precisely the range. It was the set of all output vectors. A times C, so that C is an F to the N. I call it A times X there, but of course there's a reason why I'm calling it A times C here, right? So it was set of all output vectors. When you input anything, any vector here, the output vectors, collect them together, that's the column space. That was the definition of the column space. So now here, C1, U1, Ci. So let me write this down. This is equal to, if you remember how to work out partition matrices, then this is U1, U2, Un times, this is the dot product in a partition matrix sense of C1, Cn. Such that all Ci's are in F. This is exactly the same as that. If you work it out, you see that this dot product is exactly the linear combination of the columns. Okay, but now we are done. Because now what do we have? This is exactly, well, this is the matrix A. And if I call this vector C, where instead of saying all the Ci's are in F, I could say C is an F to the N, then that is exactly what I wrote here. And so that is exactly the column space. I don't know if I should call it a proof or not, but anyway. The span of all the columns is precisely this column space, which was the definition of which was not the span of the columns. The definition I gave you was this. But now you can see that that's exactly the same. Okay, so that's where we will stop today. Today we talked about vector spaces, subspaces, examples. We did this nice condition about CW plus W prime to verify subspaces. Then we talked about the Minkowski sum and the intersection as being the supremum and infimum. Finally, we talked about the span, and we said that the span was the smallest subspace containing the set. Then we did examples of spans. Next time we will start with linear independence and then go on to basis and dimension. Okay, so that's it for today.